Hello students, we will start a new chapter on deflection of beam. So far what we have studied is about the beam is the bending stresses, shear stresses, the bending moment and shear force diagram and so on. As we know, when we apply some load on a beam, the beam get deflected into a new shape, and we have talked about the amount of bending moment that is developed, the amount of shear force that will be developed, and the calculation of bending stresses and shear stresses because of the applied load. But in the present lecture, we will talk about the deflection of the beams that will occur because of the applied loads. So here we will derive a relationship between the curvature of the beam, the deflection of the beam, and slope of the beam. Okay. So here what you can see here is we have a, let's say, a beam here, which is let's say simply supported at A and point B, and it is being applied by the external loads as shown here. Now because of this applied load, the beam will take a deformed shape. The applied load will cause the bending moment to develop in it, and because of the bending moment there will be the beam will take a new shape. And let's say this shape is shown in this another diagram here as A dash P Q B dash. So this is my new deflected shape. Okay, so here is my deflected shape of the beam. Now if we draw normal at the point P and Q of the beam, these normal are shown here as PO and QO. They will meet at point O here, and they will make, let's say, the angle d theta here. So we have drawn the normal at point P and Q, which are meeting at AO, and they are making angle d theta. So if we assume that a beam is like in a shape of a circle for a small distance between P and Q, so then OP will be equal to OQ, and that will be equal to R, or the radius of the deflection of the beam. Okay, deflected beam. If we draw a tangent at point P and Q as shown here, so we have drawn a tangent P, this tangent and this tangent. So if we draw the tangents at P and Q, it will provide you the slope of the beam with the horizontal, and it will, let's say, at point P it will make angle theta, at Q it will make angle theta minus d theta. So that is the tangents that are drawn at the point P and Q will provide you the slope of the beam. Now we know from our earlier formulas that sigma by y is equal to m by I is equal to E by R, that we have already derived. From this I can say that from this equality that 1 by R will be equal to m divided by EI, where m is the bending moment, EI is the flexural rigidity, E is modulus of elasticity, I is the moment of inertia of the beam, area moment of inertia of the beam, and 1 by R will be the basically curvature of the beam. Okay, now from the figure we can say that this chord PQ will be equal to R times of d theta, right? Because R is the radius, d theta is the angle which it subtends, so PQ will be equal to R times of d theta. So we can say from the equation 2 that 1 by R will be equal to d theta by PQ. And what is PQ? PQ is the small elemental length along the x-axis. We are assuming that this is very small. The distance between P and Q is very small, and let's say it is equal to dx. So 1 by R will be equal to d theta by dx. Now as we know that because this is the x and y axis, we are taking x axis along the length of the beam and y axis is perpendicular along which the deflection is happening, that dy by dx is equal to tan theta, that is slope. And for very small angle of theta, we can say that tan theta is approximately equal to theta. So therefore if we differentiate it with further with respect to x, we can say that d square y by dx square will be equal to d theta by dx, that is change in the slope. Now as slope decreases with the increase of dx, we see that here the slope was theta, and with the increase in the value of x, it decreases from theta to theta minus d theta. So slope is decreasing with the increase of dx, therefore d theta by dx is negative here. So we can say that 1 by r, from equation 3 we can say that 1 by r is equal to minus d theta by dx. So from equation 5 and 6 we can find out that d square y by dx square is basically equal to minus 1 by r. So we have equated the expression of equation 6 with equation 5, and we have found that d square y by dx is equal to dx square is equal to minus 1 by r. But here we have said that 1 by r is equal to m by ei. So for 1 by r we will substitute m by ei here, and we will obtain the next equation, which will say that d square y by dx square is equal to minus m divided by ei. So therefore you can say that ei d square y by dx square is equal to minus m. So this is our main equation that we were trying to derive, and we will use it for further finding the deflection of the beam. How can we do it? We can use the double integration method. So we will integrate it first, then we will get equation in slope, that is ei dy by dx equal to minus integration of m dx plus c1, and if we integrate it further we will get the value of deflection y, which is eiy minus double integration of m dx plus c1x plus c2, where c1 and c2 are the constants of integration whose values we are going to determine by using the boundary conditions of the beam. So this method, in which we derive or determine the deflection of the beam by doing 2 times the integration of the equation 8, is termed as double integration method, and we use it for the finding of the deflection of the beam. Now before we go further, let's look at the sign convention that we are going to follow here. So x is taken as positive from left to right, that means from origin to the right hand side the values of x is positive, and deflection y is positive downwards. Okay, so the y is taken as downward positive, x is taken as positive from left to right. Bending moment m will be considered positive when the beam is having a sagging shape. So if the beam is taking a smiley shape as shown here, so this is a sagging shape here, it is making a smiley face. So in this case we will take the bending moment to be positive. In case the beam is deflecting like this or opposite to this in drooping phase, then we will consider the bending moment to be negative. So our x is positive from left to right, our y is positive downward. The bending moment is positive when it is sagging. So when it is making a smiley face, we are going to say that the bending moment is positive. Okay, the slope theta is positive if we go from left to right. The tangent to the elastic curve is inclined downwards. So what is the meaning of that? So here if you see, if you are going from the left to right, that means from a dash we are moving towards the b dash, we see the slope here, the tangent is coming downwards, okay, in the downward direction. So that's why these slopes theta or theta minus d theta are termed as positive, while if you go on this side and you draw the tangent here, you will find that the tangents are going upwards. So that's why your slope will be considered on this side as negative. So slope here on the left hand side part, from the center to the left hand side part will be positive, and from center to the right hand side part will be negative as per its sign convention. Now let's look at specific cases. Let's start with the case of a cantilever beam which is having a point load at the tip of the beam. We want to determine the deflection equation for this beam, as well as we want to find the maximum deflection of the beam, which obviously we can see will occur at the tip of the beam. So let's consider a section xx dash at a distance x from the fixed end. So here in this figure you can see this section xx dash, this is my section xx dash, and we are considering it at a distance x from the origin or from the fixed end of the beam, and there is on this beam there is a deflection, there is a point load W acting at the tip of the beam. So the bending moment in this case at the section XX will be given by the value of load W, this load W, and multiplied by the distance of this load from the section XX. So the distance of the W from section XX dash will be W into L, will be the L minus X. So the load will be W into L minus X. Now as this beam is making a drooping phase, okay, it is going downward. So as per our sign convention, it is a negative bending moment. So we'll substitute a minus sign here, put a minus sign here. So our bending moment equation mx will be minus W into L minus X. Now from the equation 8, we have already find out that EI times of d square y by dx square equal to minus m. So we'll substitute for m the value of W into minus W into L minus X. So it will give us EI d square y by dx square equal to W into L minus X, or WL minus WX. Now we'll go with our double integration method. First we'll integrate it. So with respect to x, so okay, please make a correction here. This is d square y by dx square. Okay. So if we integrate it with respect to x, so it will give us EI dy by dx equal to integration of WL will be WLX, and integration of WX will be WX square by 2. Okay, and plus a constant of integration C1. Now at point A, which is the fixed end of the beam, we know that x is equal to 0 here, and because the end is fixed, there will be no slope of the beam at this point, so the dy by dx will also be 0. So in the case of a cantilever beam at the fixed end, the slope is always 0. So this gives us, if we substitute x equal to 0 here in the above equation and dy by dx equal to 0 here, so this is going to give us C1 equal to 0, right? So finally we get the equation as EI dy by dx equal to WLX minus WX square by 2. Now this is the equation for our slope. We can, by this equation we can find the slope along the length of the beam at any point, but our objective is to determine the deflection of the beam. So we will integrate this equation further, and this will give us on the left side as EY, and integration of WLX will be WLX square by 2, and WX square by 2 the integration will give as minus WX cube by 6 plus a constant of integration C2. Again we'll look at the fixed end. At A, we know that when x equal to 0 at the fixed end, y deflection is also 0. So at fixed end there is no deflection. So if you substitute x equal to 0 in these two terms and y equal to 0, this is going to give us C2 also equal to 0. So if we substitute this here, we will get the equation for the slope. So this is our equation of slope, by which we can determine the slope value along the length of the beam at any point from x equal to 0 to x equal to L. As we know that the maximum deflection of the beam is occurring at the free end, which is at x equal to L. So y max will be obtained by substituting x equal to L in this equation, and this is going to give us the value of y max as WL cube over 3EI. So this is the maximum value of deflection that we'll obtain, and W is the point load that is applied, L is the length of the beam, and E and I we are familiar, that is effective rigidity of the beam. Now let's look at the next case. This is the case of a cantilever beam with uniformly distributed load. So here you can, in this figure you can see a cantilever beam AB, and it is subjected to a uniform load of W per unit length. Okay, so the load value is given as W per unit length, and the length of the beam is L, and we are considering a section XX dash at a distance x from the fixed end, that is A, which is where x equal to 0. So we are considering a section XX dash at distance x from the fixed end A. Obviously again the maximum deflection will occur at the free end, which is at B. So here it is shown as y max. Now at the section XX dash, our bending moment equation will be the load multiplied by the distance, and in this case the load value will be W into L minus X. So we are considering the load of this portion. So this portion will provide us the load value. W per unit length is the load, so the length is L minus X, so W into L minus X is the value of the load. And now the distance at which this load is acting from section XX dash. So as we know, well, we were making the calculation for bending moment and shear force diagram, that for the uniformly distributed load we can assume the load to be acting at the middle of the length of the beam for which we are considering it. So that distance will be L into L minus X divided by 2. So the load value WL minus X multiplied by L minus X by 2 is going to give us the bending moment at section XS dash. We have done this exercise in case of BMSF diagram. I hope you must have remembered it. So from our equation of EI d square y by dx square equal to minus m, we substitute the value of m here. And you see here we have taken a negative sign in front of m because this is a drooping shape. So this is our sign convention. So we have taken a negative sign here. So this finally gives us EI d square y by dx square equal to w into L minus x whole square by 2, which you can open it further here and obtain this expression as shown here. Now we integrate this expression, which going to give us the equation for slope EI dy by dx, that equals to w by 2 into L square x minus Lx square plus x cube by 3 plus constant of integration C1. Now is the time to apply the boundary condition. So at fixed end A, the deflection x equal to, which is at x equal to 0, our slope dy by dx is 0. So when you substitute x equal to 0, x equal to 0 here, and dy by dx equal to 0 here, this will provide us C1 equal to 0. So first constant of integration is 0. So you substitute back this into the above equation and you get this expression, which you integrate it further in order to obtain the equation for slope. So on the left side we get E into EI into y, and the right side we get this expression along with the constant of integration C2. Again we apply the boundary condition at A, where x is equal to 0. Our deflection is also 0 in the case of cantilever beam. So when you substitute x equal to 0 in these three terms and y equal to 0 here, this is going to provide us C2 equal to 0 here. So now the second constant of integration also turns out to be 0. So finally our equation for deflection will be obtained as shown here. So by this equation we can calculate the deflection of the beam at any point from x equal to 0 to L by substituting the particular value of x. Now we want to calculate the maximum deflection of the beam, which will incidentally occur here at also at the free end. So at free end we know that x is equal to L. So we substitute for x equal to L here in these expressions. So you will get L4 by 2 minus L4 by 3 plus L4 by 12 here, which you can calculate and find that Y max will turn out to be W L4 divided by 8 EI. Remember, this W is the uniformly distributed load. So load per unit length, the unit of it is kilonewton per meter or maybe Newton per meter. So that W is the load per unit length. So that's why you get the Y max as WL4 divided by 8 EI. Now our third case, this is the case of simply supported beam with point load at the center. So as you remember that in case of finding out the bending moment for such cases, we first need to determine the reaction of the beam in the case of simply supported beam. This is a symmetrical beam and load being applied at the exactly at the center. So the reaction at RA will be equal to RB will be equal to simply W by 2. Half of the load will be shared at each of the support. So this is the beam AB, which is subjected to a point load exactly at the center, and we'll consider this section XX at a distance x from the left end A. So the bending moment at this point will be equal to the reaction force RA multiplied by the distance x. So RA is equal to W by 2, and that multiplied by x is going to give us the bending moment. Now this bending moment, as per our sign convention, will be taken as positive because it is going to make this smiley face. So because of this sagging shape, I would say we are going to call it as positive bending moment. So mx will be equal to W by 2 into x. Now let's utilize our equation as before. So EI d square y by dx square is equal to minus m. So you substitute their value of m as W by 2 into x, and then you integrate this equation to obtain the equation for slope as EI dy by dx equal to minus W x square by 4 plus constant of integration C1. Now here in this case, in order to determine the value of constant of integration, we will use the midspan value of slope. You see here that exactly at the middle of the beam, if you draw the tangent here at this point, our slope is 0. So because at this point exactly at the middle of the beam the slope is 0, so dy by dx is 0. So at x equal to L by 2, exactly at the middle of the beam, Here dy by dx is 0. So for here substitute x equal to L by 2, substitute 0 here. So this is going to give us equation as like shown here, which will provide us the value of first constant of integration as WL square by 16. You substitute it back here in this equation and you can obtain this equation as shown here. EI dy by dx equal to minus wx square by 4 plus WL square by 16. We will integrate this equation further to obtain the slope the deflection equation. So on the left hand side it will give us EIY. On the right hand side we will get this expression along with the constant of integration C2. This time we know that at the fixed end, or rather at the support end, rather I would say, not at the fixed end, but at the support end A, x is equal to 0 and also the deflection is 0 because it is being supported at the point A. So our deflection is 0 at the point A. So when you substitute x equal to 0 in these two expressions and y is equal to 0 here, this will provide us C2 will be equal to 0. So we substitute the value back of the C2 equal to 0 and we get the expression for y as 1 upon EI with the bracketed term which is shown here. Now the maximum deflection of this beam will occur exactly at the middle of the beam where x is equal to L by 2. So we substitute x is equal to L by 2 and obtain the maximum deflection by substituting x equal to L by 2 here and x equal to L by 2 in this expression, which will give us this bottom expression, and which we calculate and simplify, then it is going to give us the y max value as WL cube over 48 EI. So this expression gives us the maximum deflection which is at the center of the beam of a simply supported beam with a point load at the center as WL cube divided by 48 EI. Now the last case of today that we are going to consider is simply supported beam with a uniformly distributed load. So you can see here the beam AB is subjected to uniformly distributed load of W per unit length along the entire length of the beam. Exactly at the middle span we are going to see there will be maximum deflection which is at x equal to L by 2 from the left end. In order to derive our equation, let's consider the section XX dash which is at a distance x from the left end A. So what will be the value of the bending moment here? Where we have done the BMSF diagram case, so we know that first we need to determine the reaction at point A and B. So RA will be R equal to RB, that is equal to half of the load that is entirely acting on this beam, that is W into L divided by 2. So because W is the load per unit length multiplied by the length of the beam is WL, that is the total load that is acting, and it will be simply shared equally by both left and right hand support. So it will be reactions will be WL by 2. Now the bending moment will be RA into X, so that is WL by 2 into X minus, this is the bending moment acting in the clockwise direction, but now there is an anti-clockwise movement because of the applied load which is in this area, so that is W into X and multiplied by the distance at which it is acting. So we can consider it to be acting at half of the distance from the total length of the beam on the left hand side, so that is x by 2. So that gives us my x wx square by 2. So our expression for bending moment will be WL by 2 into x minus wx square by 2. We substitute it into our expression for EI d square y by dx square equal to minus mx. So we will substitute it over here and we'll obtain the expression as shown here. Remember we have taken a positive here description for the bending moment because again we are getting this smiley face here. So our bending moment is considered positive. So we'll get this expression here which we are going to integrate with respect to x and obtain the expression as shown here, WLX square by 4 plus WX cube by 6 plus constant of integration C1. Again as before we have done for the simply supported point load case, we will consider at x equal to L by 2 our slope is 0, dy by dx is 0. So exactly at the middle of the beam, if you draw the tangent, it is having the 0 slope. So you substitute x equal to 0 in these expressions and dy by dx equal to 0. This will provide us, x equal to L by 2 here in these expressions and dy by dx equal to 0. This will give us the value of constant of integration C1 as WL cube by 24. Let's substitute this expression back into the previous equation as C1 value and we integrate further with respect to x, which will give us the value of deflection EI, the value of deflection y as EIY minus this expression plus constant of integration C2. Now for the boundary condition here, that at x equal to 0, that means at the support end, we know that the slope is 0. So this will give us C2 equal to 0. So you substitute x 0, 0, 0 and 0 here. This is going to give us C2 equal to 0. So second constant of integration is 0. This gives us the finally the equation or the expression for the deflection of the beam along the x. So the maximum deflection, as we know, that will occur at the exactly at the center of the beam. So at x equal to L by 2, the maximum deflection will be there. So we substitute x equal to L by 2 in this expression, and you can obtain the maximum value of deflection as 5WL4 divided by 384 EI by substituting x equal to L by 2 here. So this brings us to the end of this lecture. So we have done this part of the double integration method for the deflection of the beam.